All right, here we go again. Lesson 8.3, evaluating logarithms. I want you to recall from lesson 8.1, we graphed a exponential function, and then we graphed its inverse by taking our table of values for our exponential function and flipping x and y to graph the function's inverse, which turned out to be the logarithmic function. What we know from inverse functions, specifically our trig inverse functions, is that the inverse function undoes the original function. So if we look here, when we had sine of, say, theta equal to 1, if we wanted to figure out what theta was, we took the inverse of 1, and that gave us our angle theta, or it gave us the input to our original function. Logarithms work quite the same way, and that we remember from our relationship between exponents and logarithms that if we had, say, a base b raised to an exponent y, that would equal a number, and its relationship with a logarithm was that the logarithm of the same base b, but this time of x, gave us the exponent. So the logarithm gives us the input to our exponential function, just like sine inverse gives us the input, the angle, to our sine function. So there's your relationship. How do we use that relationship to evaluate logarithms? Well, we actually use that definition to look for the exponent that we would have to raise each base to give us our value inside the logarithm. So let's try one. We have the log of 64 base 4. If we rewrite this as an exponent, we're looking for 4 to the exponent x equals 64. Or to what exponent do we have to raise 4 to get 64? Mathematically, how we would solve that is we'd look for what exponent we have to raise 4 to get 64. So 4 to the exponent what? Well, if we think about our powers of 4, 4 to the power of 1 is 4, to the power of 2 would be 16, and to the power of 3 would be, hey, 64. So there now we have two powers with the same base. We can equate the exponents, and we get x equals 3. So we've just solved that logarithm. We can do similar with b. Set our logarithm equal to x and rewrite it as a power. So 3 to the power of x equals 1 over 27. This one's trickier because we have a fraction. If we think of 27 as a power of 3, it would be 3 to the power of 1 is 3, to the power of 2 is 9, to the power of 3 is 27. So we would have 1 over 3 to the exponent 3. And if we think about our negative exponent rules, we can re-express 1 over 3 to the exponent 3 as 3 to the exponent negative 3. Which then, if we equate our exponents, gives us our answer. X equals negative 3. So the log of 1 over 27 base 3 is negative 3, because 3 to the exponent negative 3 is 1 over 27. All right. That works really well if you can change the base of a number to express it as the same base as your logarithm. But if you can't do that, we have to come up with some other strategies. So if we look at our next example, we have the log of negative 4 base 2. If we try the same strategy, we would equate it to x, rewrite it as a power, so 2 to the exponent x equals negative 4. And then we'd ask ourselves, how can we rewrite negative 4 as 2 to the exponent something? So we can match it with our other power. If we think about our exponents, if we use negative 2 as our y, that would give us 1 over 4. If we use negative 1, it gives us 1 over 2. If we use 0, it gives us 1. If we use 1, it gives us 2. And if we keep going, we don't actually find a value that gives us negative 4. And the reason is, if you think about the exponential function 2 to the exponent x, does it equal negative 4? Well, a quick sketch might remind you that that graph has a horizontal asymptote, and the function raises up to the right. So if we graph it, we can see that, well, that function is actually never negative, it's only positive. So therefore, in this example, we have no solution. There is no solution because the domain, sorry, not the domain, the range of our exponential is that y must be greater than 0. So your strategy that you can use when you can't rewrite those powers with a common base is to think about the graph and make sure that the value you're actually looking for is within the range. There's a couple other strategies, but we'll touch on those in a second. So example D. Example D is the log of root 3, or sorry, 25 root 3 with a base of 5. And if we set that equal to x, we can rewrite it as a power. That power would be 5 to the exponent x equals, not root 3, the third root of 25. And our first strategy was to try to rewrite it as a common base. And it's quite difficult to see how you could do that maybe directly here. So if we apply some exponent rules, I'm going to rewrite that third root as an exponent. And that exponent would be 1 over 3. So now it might be a little bit easier to see how we're going to rewrite 25 as a power of 5, because 5 to the exponent 2 is 25. And if we have a power of a power, exponent rules tell us to multiply those powers. So we would get 5 to the exponent 2 times 1 over 3 is 2/3. And now we can equate the exponents. X equals 2 over 3. So the question was, to what power do we have to raise 5 to get the third root of 25? And the power is actually, or the exponent is 2 over 3. The next one might look familiar from our first lesson, because that's a natural logarithm. Sorry, not a natural logarithm, the common logarithm. That's a log base 10 of 1,000. So the question is asking us, to what exponent do we have to raise 10 to get, oh, it's not 10,000, it's 1,000, sorry. To what exponent do we have to raise 10 to get 1,000? And for a question like this, basically we're just counting the zeros, because there's 3 zeros and 10 to the exponent 3 is 1,000. So the answer to our question, what exponent do we have to raise 10, not 16, to get 1,000 is, well, 3. So x is 3. So if we can make a common base, go for it. Make yourself a common base. If we can't, make sure the value we're looking for is actually in the range of the function. But f actually gives us a new wrench in our process here. We have the log of 47 base 5. You might be able to see the problem already, you may not, but let's rewrite it as an exponent first. 5 to the exponent 7 equals 47. And now our goal would be to write 47 as a power with a base of 5. And if we think about our powers of 5, 5 to the exponent 1 is 5, to the exponent 2 is 25, to the exponent 3 is 125. So actually the answer is somewhere between 2 and 3, but we can't directly get to it. So there's a couple strategies that we could use here. The first one is to guess and check. And you would have to go through the process of plugging in values of x until you find one that gives you 47. And we'd probably look for an accuracy of maybe 1 decimal place. We know it's somewhere between 2 and 3, so we tried numbers like 2.1, 2.2, 2.3 until we came up with one that was close to 47. Aside from guess and check, we could use graphing technology. And to graph this, we would actually graph two things. We'd graph 5 to the exponent x as an exponential function, and we'd look for where it is equal to 47. So we'd graph y equals 47 as well. we look for where those two functions are equal, which means we're looking for the point of intersection. So two strategies. In the future, we're actually going to come up with a easier strategy. There are actually two easier strategies. One is to change the base of the logarithm, and we're going to look at that in a future lesson. And another one is to use an advanced calculator, and some of the calculators that you have are advanced enough to actually enter this logarithm and evaluate it. So an advanced calculator. But for now, basically we have three strategies for evaluating a logarithm. The first is to use the definition of a logarithm. So by converting to an exponent, or sorry, a power. The second would be to use graphing technology. And the last is actually just to use guess and check. So for now, those are your three strategies. I want you to use one of those three. Ideally, the first strategy when possible. If not possible, we'd be using graphing technology in class. If it was to show up on an evaluation, you would have to use guess and check. Okay, that's it for the first part of lesson 8.3.